All right, so let's have the continuation of our discussion on patterns and nonlinear functions. And this time, we will be having this scenario, okay? Wherein we have a table and it shows the number of blocks in each figure. So this is the figure that we have. So we have only one block, and then you have two, and then three. And for each number of blocks in the edge, on the edge, we are actually counting how many are the total blocks in it, okay? So if there's only one block on edge, then there's only one total in here. If there are two on the edge, so as you can see, one block here, and then this is the second one, so there's two of them. But all in all, there's a total of 8 blocks in there. So if you have 3 in here, 3 on the edge, there's a total of 27 in there. So we need to know, or what we need to find, what will be the number of total, what's the total number of blocks if there's 4 blocks on the edge and then 5 blocks on the edge. All right, so we need to find those total number of blocks, and then a corresponding ordered pairs. So we need to represent the relationship of the number of blocks on the edge and the total number of blocks. We have to represent it on the graph and also using words. All right, so if you're going to take a look here, if you have a total of 4 on the edge, okay, so try to look at the patterns here. 1 stayed as 1, 2 became 8, all right, and then 3 became 27. So if you're going to take a look at the pattern, you will notice a few things, okay? How can you make 2 to become 8? Well, there are several ways on how you can do that, okay? You actually have 2 times 4, excuse me. So you can have it as 2 times 4, correct? You can have it that way. Another way for you to generate an 8 from a 2 is it could be 2 to the 3rd power, all right? So now, because of those 2 options that we have, let's try to apply it with our 3, okay? So if we apply times 4, definitely 1 times 4 is not gonna work, okay? So we can check 1 to the 3rd power. Is it equal to 1? Yes. All right, so that's a possibility. Now we can check it with 3 as well. 3 to the 3rd power, is it going to be 27? And it's a yes. So as you can see, because all of these 3 numbers here, all these 3 outputs here can be generated if we cube our number of blocks on the edge, then we can conclude that this missing number here could be 4 to the 3rd power. And what will be 4 to the 3rd power? So that's 4 times 4, 16 times 4, which is going to be 64. Okay, so if there are 4 blocks on the edge that you can see, there's going to be a total of 64 blocks all in there. Which means if it is 5, okay, so 5 to the 3rd power is 5 times 5, 25 times 5, that's going to be 125. And so our point here would be 5, 1, 25. And if you're going to plot these points here, so 0, 0, of course, 1, 1, it's going to be somewhere here. Sorry, 1, 1 is there. Okay, you have 2, 8. 2, 8 is gonna be somewhere here. So this is 50, middle 1, 2, 3. So that's around 25. So I'm gonna say 2 will be 8 over here somewhere. Okay, and then 3 is 27. So it's gonna be somewhere above the half of this. So probably over here. And then you have 4 will be 64, so 64 is gonna be somewhere over here already. And then 5 is 125, that's gonna be way up here already. Oops, sorry. Okay, so that is the graph. That's a really steep curve over there. Okay, and so when we try to describe this in words, the total number of blocks, so y, our equation I should say, first y is going to be equal to the number of blocks on the edge. We simply just have to cube it, raise it to the third power. Okay? All right. So let's have this next example. So pretty much similar to the previous example. So I would like you to try and see what relationships you are seeing. So I would like you to predict what the missing numbers here and what will be the equation that could best describe this pattern. So go ahead, try it out. All right, so what you can notice here is that, okay, so there are 3 new branches here, and how many branches is it attached to? To just one, right? So it's pretty much like 3 times 1, okay? Let me just get that up here. So that's just 3 by just 1 here. Now, how many 3's are you seeing here? So the new branch, that's 3, and then it is multiplied to 3 old branches, okay? And then for the other one, you will see here, it's 3 times this 3 over here, times this 3 other branches here. So it's like 3 times 3 times 3. And so if you will see the pattern, if you add 3 more to each of these small red branches here, you know it's going to be 3 times 3 times 3 times 3. So this, you're multiplying, actually what's happening here is that you are multiplying 3 by the number of figure, okay, by the number of original branches. So this is 3 to the first power, 3 to the second power, this is 3 to the third power, which means when we head to 4, this value here is simply 3 to the fourth power, and that will be 3 times 3 times 3 times 3, which is 81. And getting 3 to the fifth power, that is going to be 81 times 3, which is 243. So just like what we have observed here, the pattern that we are seeing is that the number of new branches, which is y, will always be equal to 3 raised to the number of figure. So this is figure 1, figure 2, figure 3, and those are the original branches. Okay? All right.